Greetings, citizens of the world. This is Anonymous. We speak to you today with a warning. Scientists are now reviving viruses that have been locked in permafrost for tens of thousands of years. Some of these samples have been brought back to life after lying dormant for more than 48,000 years. These so-called zombie viruses were never meant to see the light of day again, and yet they are being handled as if they pose no risk to humanity. The Siberian permafrost has preserved pathogens from an ancient world, viruses that predate our understanding, our immunity, and our medicine. Among them could be strains similar to pox viruses, or others that once had devastating effects on human populations. Scientists warn that the melting of permafrost may release some of these naturally, but to deliberately revive them in laboratories is to play with fire. Despite what is being told to the public, the truth is simple. We do not know what the full consequences of this research could be. Humanity is still reeling from recent global events that shook trust in institutions. People are right to ask whether energy and resources should be directed toward healing the planet, feeding the hungry, or providing clean water, instead of awakening viruses from an age before history. To those who justify this work in the name of science, know this: not every discovery benefits humanity. Sometimes restraint is wisdom, sometimes caution is survival. We are Anonymous. Expect us.
Throughout the history of humanity, one of the greatest struggles has been the battle against disease. Entire civilizations have been weakened, reshaped, or even erased by viruses that spread faster than our ability to defend against them. From the earliest plagues to more recent outbreaks, the destructive potential of viruses has always been a stark reminder of our vulnerability. For this reason, the idea of deliberately reviving ancient viruses that have remained frozen in permafrost for tens of thousands of years is not only reckless, but poses risks that we cannot fully comprehend. The Siberian permafrost has acted as a natural freezer, preserving remains of plants, animals, and microorganisms that existed in climates and ecosystems long gone. Among these preserved remnants are viruses, some of which have already been reawakened in laboratory settings after lying dormant for as long as 48,000 years. Scientists argue that such studies are valuable for understanding viral evolution, resilience, and the history of life on Earth. However, the dangers far outweigh the potential benefits. These are viruses from a time when humanity had never encountered them, pathogens that may be completely foreign to our immune systems. To expose modern populations to such organisms is to gamble with forces we neither control nor fully understand. One of the most pressing concerns is the complete unpredictability of how these viruses might interact with human biology. Our immune defenses evolved in response to known pathogens over millennia. Introducing viruses that were last active during the Ice Age could present entirely novel threats to our health. Modern medicine, vaccines, and antiviral treatments are designed around the pathogens we know today, not organisms from tens of thousands of years ago. If such a virus were to escape containment, humanity could be confronted with an outbreak for which there is no pre-existing treatment or defense. Another danger lies in the possibility of these ancient viruses adapting rapidly once exposed to modern hosts. Viruses are notorious for their ability to mutate and evolve. A pathogen that has been dormant for millennia could, once reactivated, undergo changes that allow it to spread in ways no one anticipated. Even if initial tests suggest that a virus poses no immediate threat to humans, the very act of reviving it and exposing it to laboratory conditions could alter its properties, making it more dangerous. The consequences would not be limited to humans alone. These ancient pathogens might also affect animals, plants, or even microorganisms within ecosystems, triggering chain reactions that destabilize environments. A virus capable of infecting wildlife could spread beyond control, creating ecological disruptions with effects that ripple through food chains and ecosystems. Humanity has already witnessed how the introduction of new diseases into unprepared populations can devastate entire groups of people or wipe out species. Reviving viruses from the distant past risks repeating this tragedy on a far larger scale. Furthermore, the argument that reviving these viruses helps us prepare for potential outbreaks caused by thawing permafrost is deeply flawed. It is true that global warming is accelerating the thawing of Siberian permafrost, raising the possibility that ancient pathogens could re-emerge naturally. However, the deliberate act of reviving them in laboratories and experimenting with them significantly increases the chance of accidents. Human error, equipment failure, or breaches in containment are not rare occurrences. History has shown that even in highly secure facilities, accidents happen. The potential consequences of an ancient virus escaping a laboratory are not something humanity should risk. In addition to the biological risks, there is the ethical dimension. Science is not carried out in isolation. It has consequences for societies and individuals. To deliberately bring back viruses that humanity has never encountered before is to make a decision on behalf of billions of people without their consent. Communities who already carry the weight of environmental and health crises should not be further endangered by experiments whose outcomes are uncertain and whose risks could be catastrophic. This raises serious questions about responsibility, accountability, and the moral boundaries of scientific inquiry. Moreover, the pursuit of reviving ancient viruses often distracts from more pressing global challenges. Humanity today faces urgent crises, including deforestation, pollution, food insecurity, and emerging diseases that already exist. Resources invested into awakening viruses from prehistory could instead be directed toward combating these real and present dangers. The revival of ancient pathogens does not heal the sick, does not feed the hungry, and does not protect vulnerable communities from the environmental disasters unfolding around them. Instead, it risks introducing entirely new problems into a world already struggling with enough. There is also the possibility of misuse. Once a virus is revived and studied, the knowledge and techniques associated with its revival could be misapplied. In the wrong hands, these viruses could be weaponized or used irresponsibly. Scientific knowledge is powerful, but not all who wield it use it wisely or ethically. By reviving ancient viruses, researchers may be creating tools that could be turned against humanity in ways they never intended. History provides sobering lessons about unintended consequences. Time and again, technologies and discoveries celebrated as breakthroughs have also produced unforeseen dangers. Nuclear research gave rise not only to energy production, but also to weapons capable of destroying cities. The manipulation of ecosystems often resulted in invasive species and environmental collapse. The revival of ancient viruses has the potential to follow a similar path, a discovery made in the name of science that instead unleashes consequences far beyond our control. The sheer age of these viruses should give pause. If a virus has remained viable after being frozen for tens of thousands of years, its resilience alone is remarkable and frightening. It suggests that these organisms are capable of enduring extreme conditions and remaining infectious across vast stretches of time. To underestimate such resilience is to invite disaster. Humanity is not prepared to face pathogens that have already survived epochs of environmental change. Scientists have found that Pacific Islanders are carrying the DNA of an unknown human species. Recent scientific findings have revealed genetic traces suggesting the existence of an unknown and now extinct human lineage within the DNA of present-day Melanesians, who inhabit the South Pacific region situated to the northeast of Australia. This groundbreaking discovery has ignited considerable interest and speculation within the scientific community, as it provides potential insight into the intricate tapestry of human evolution. Based on recent genetic modeling, the analysis indicates that the species under scrutiny does not align with the Neanderthal or Denisovan lineages, both of which have been well documented in the fossil record. Instead, it potentially signifies a third, as yet unidentified human ancestor, which has hitherto remained undiscovered by archaeologists. This finding suggests a deviation from the existing known spectrum of human evolution and calls for a comprehensive reassessment of our understanding of ancient humans. Ryan Bolender, a statistical geneticist at the University of Texas, emphasized that there is a significant gap in our understanding of population dynamics, or possibly a misinterpretation of relationship dynamics. This observation suggests that there are critical factors that may be overlooked or misconstrued in existing research. Bolender and his research team have dedicated their efforts to analyzing the proportions of ancient hominid DNA that are still present in the genetic makeup of present-day humans. Through their studies, they have uncovered disparities in prior assessments, indicating that our interactions with Neanderthals and Denisovans may not fully account for the genetic variations observed in modern humans. It is believed that approximately 100,000 to 60,000 years in the past, our ancient forebears undertook a migration from Africa, subsequently encountering other hominid species inhabiting the Eurasian landmass. The influence of this interaction has had a lasting impact on humanity, as evidenced by the presence of unique genetic markers from Neanderthals in the DNA of present-day Europeans and Asians. This genetic legacy serves as a testament to the historical intermingling of our ancestors and Neanderthals. A few years back, a group of researchers delved into the study of specific genetic variations originating from Neanderthals that have been passed down to individuals of European ancestry. Their findings revealed a link between these genetic markers and various health issues, such as heart attacks and certain skin ailments. Furthermore, the research also suggests that these inherited variants may play a significant role in predisposing individuals to these health conditions. A recent study has presented compelling evidence indicating that contemporary human papillomavirus were transmitted through contact to Homo sapiens subsequent to interbreeding between our ancestors and Neanderthals, as well as Denisovans subsequent to their departure from Africa. Extensive research has been conducted on our association with Neanderthals. However, our interactions with the Denisovans, who are the distant relatives of Neanderthals, remain somewhat ambiguous. The challenge lies in the fact that while the fossil record offers a wealth of information about Neanderthals, with numerous remains unearthed throughout Europe and Asia, the Denisovans are represented by only a solitary finger bone and a few teeth discovered in a Siberian cave in 2008. This scarcity of Denisovan remains contrasts sharply with the extensive presence of Neanderthal fossils, presenting a significant disparity in our understanding of these two ancient human groups. In an in-depth exploration, utilizing an innovative computer model to estimate the proportion of Neanderthal and Denisovan DNA present in present-day humans, Bolender and his research partner determined that both Europeans and Chinese individuals harbor a comparable quantity of Neanderthal DNA, approximately 2.8%. This research offers a comprehensive understanding of the genetic heritage of these populations, shedding light on the intricate interplay of ancient hominins and modern humans. The outcome aligns closely with findings from earlier research, which have suggested that individuals of European and Asian descent typically harbor approximately 1.5 to 4% of their DNA from Neanderthals. When researchers delved into the Denisovan DNA, they encountered greater intricacy, especially concerning present-day populations in Melanesia. This region, encompassing Vanuatu, the Solomon Islands, Fiji, Papua New Guinea, New Caledonia, West Papua, and the Maluku Islands in the South Pacific, presented a more complex scenario. While the absence of certain species in the fossil record may lead us to believe they never existed, the reality is that preserving organic remains for tens of thousands of years is an immensely challenging task. Subsequently, the fortuitous alignment of favorable conditions and timing is essential for the excavation of such remains. As we delve deeper into the genetic composition of our oldest societies, we anticipate uncovering additional clues about the intricate and diverse history that our species has in common with those that have not survived into the present era. This exploration will likely provide insights into the shared experiences and interactions between our ancestors and ancient societies, unraveling the rich tapestry of human history. The findings of Bolender's examination were showcased at the annual 2016 American Society of Human Genetics gathering. Artificial intelligence study of the human genome finds unknown human ancestors. In delving into the intricate narrative of the complex origins and evolution of our species, it becomes apparent that a multitude of factors contribute to this fascinating story. A recent research endeavor utilized the power of machine learning technology to meticulously examine 8 prominent human origin and evolution models. Through this process, the software succeeded in identifying compelling evidence within the human genome that points to the existence of a ghost population of human ancestors. The comprehensive analysis indicates the likelihood of a previously undiscovered and now extinct group of hominins engaging in interbreeding with Homo sapiens in the regions of Asia and Oceania at some point during the intricate course of human evolutionary development. These interactions have left behind only fragmented remnants in the DNA of modern humans, shedding new light on the ever-evolving tapestry of our species' history. The research, which has been documented in the prestigious journal Nature Communications, represents a pioneering effort in demonstrating the potential of machine learning in unraveling the mysteries surrounding our ancestral lineage. Through meticulous analysis of extensive genomic data, extracted from ancient fossilized remains and its correlation with the DNA of contemporary humans, researchers are initiating the process of bridging the lacunae in the evolutionary narrative of our species. This innovative approach promises to provide profound insights into the intricate pathways that have shaped the history and development of humankind, shedding light on fundamental aspects of our genetic heritage that have long remained obscured. The findings in this instance appear to align with theories in paleoanthropology that have been formulated based on the examination of fossilized human ancestors unearthed from the Earth. The recent data indicates that the enigmatic hominin is likely the result of a blend of Neanderthal and Denisovan ancestry. Denisovans were only classified as a distinct species on the human evolutionary tree in 2010. This particular species in our ancestral lineage would bear a significant resemblance to the fossil of a teenage girl from Siberia's Denisova cave, dating back 90,000 years. Her remains were identified last summer as the sole documented case of a first-generation hybrid between the two species, with a Neanderthal mother and a Denisovan father. This revelation significantly contributes to our understanding of human evolution and the intricate interplay between different hominin species across millennia. Study co-author Jaume Bertrand-Petit, an evolutionary biologist at Barcelona's Pompeu Fabra University, emphasizes that the discovered individual aligns with the expected characteristics of the population's origin. However, he underlines the significance of this not being attributed to a solitary individual, but rather to an entire population. The analysis of the human genome in previous studies has shown that once modern humans departed from Africa, approximately 180 years ago, they engaged in interbreeding with other hominin species, such as Neanderthals and Denisovans, who coexisted with early modern humans before eventually becoming extinct. However, incorporating these distinct branches into our ancestral lineage has posed significant challenges. Substantiating the existence of these ghost species has been hindered by limited evidence, leading to various competing theories regarding the timing, locations, and frequency of interbreeding between Homo sapiens and other species. This complex phenomenon has sparked numerous debates, underscoring the need for a more comprehensive understanding of the interconnections among early human populations and their interactions with other hominin species. Through ancient interspecies unions, known as introgressions, distinctive points of divergence within the human genome can be discerned. Scientists have observed a greater genetic variance between certain chromosomes than anticipated, if both had originated solely from the same human species. Following the sequencing of the Neanderthal genome in 2010, it became evident that some of these divergences indicated segments of our genetic code inherited from Neanderthals. Furthermore, studies have indicated that a portion of present-day humans can trace up to 5% of their genetic lineage back to Denisovans. This illuminates the substantial impact of ancient interspecies interactions on the genetic composition of modern humans. Undertaking the task of identifying and examining the numerous varied locations across the genome and calculating the myriad genetic permutations that might have given rise to them is a daunting endeavor that surpasses the capabilities of humans alone. However, this complex undertaking may be ideally suited for deep learning algorithms. The exploration and assessment of the diverse regions within the genome, along with the computation of the extensive genetic variations associated with them, present a formidable challenge that may exceed the capacity of human efforts. Deep learning, a subset of artificial intelligence, utilizes algorithms to mimic the functionality of an artificial neural network, essentially emulating the cognitive processes observed in mammalian brains. These sophisticated machine learning systems have the capacity to recognize intricate patterns and assimilate prior data, enabling them to learn and subsequently engage in novel tasks or seek new information following the analysis of vast datasets. A prominent instance of this is Google DeepMind's AlphaZero, which demonstrates the ability to autonomously acquire expertise in various board games, thereby exemplifying the immense potential of deep learning in practical applications. This advancement in technology has paved the way for significant innovations and continues to redefine the capabilities of modern artificial intelligence. Deep learning, As explained by Joshua Schreiber, an expert in evolutionary genomics at Temple University, involves the process of fitting a more complex shape to a collection of points within a larger space. In contrast to simply fitting a line between 2 points, y and x, deep learning entails fitting a convoluted structure to a set of points in a significantly larger, potentially 1,000-dimensional space. Essentially, deep learning acknowledges the uncertainty regarding the optimal shape to fit these points, pushing the boundaries of exploration to observe the outcomes derived from this approach. In this instance, the machinery was deployed to analyze the human genome and forecast human demographics through the simulation of various potential scenarios of ancient evolution, thus envisioning how our DNA could have developed over millennia. The software took into consideration the composition and progression of DNA, alongside human migration and interbreeding patterns, in an effort to piece together elements of an exceedingly intricate puzzle. This multifaceted endeavor involved meticulously modeling the complexities of genetic evolution and human ancestry, ultimately culminating in a profoundly extensive and elaborate exploration of our genetic history and demographic projections. The team of researchers conducted in-depth training of the computer to meticulously analyze 8 distinct models, portraying the most feasible theories concerning early human evolution across Eurasia. These models were derived from prior studies, aiming to construct a scenario that would ultimately lead to the present understanding of the human genome, encompassing its identified Neanderthal and Denisovan elements. The comprehensive approach undertaken by the researchers involved a thorough exploration of the various models, delving into the complexities of each theory to gain enriched insights into the evolutionary path of humans across Eurasia. Renowned researcher Bertrand Petit highlights the existence of potential alternative models, aside from the ones currently discussed in scientific literature. These proposed models originate from the Out of Africa event and present diverse scenarios of ancestral lineage divisions involving interbreeding between recognized species and hypothetical ghost species. These models diverge in their interpretations of significant evolutionary events from the Out of Africa dispersal. The variations in lineage splits and interbreeding events encompass a spectrum of scenarios, thus contributing to a more comprehensive understanding of human evolution. Bertrand Petit's acknowledgement of these diverse models underscores the complexity of human evolutionary history and the ongoing quest to unravel its intricacies. Bertrand Petit explains that through extensive computations carried out over several weeks for each of the 8 models, they assess their proficiency in replicating the current genetic makeup of humans. Each simulation undertaken represents a potential trajectory of human evolution, and these simulations have been conducted thousands of times. The utilization of deep learning algorithms enables the identification of the models that most accurately align with the available data. The machine's analysis suggests the presence of an unidentified ancestor species in our evolutionary line. According to Bertrand Petit, the models with evidence of interbreeding from this enigmatic population are the most strongly supported by the available data. This indicates the existence of a ghost population introgression that has left an indelible mark on our genetic makeup. The thought-provoking research, along with similar studies, has the potential to redefine our understanding of the migratory patterns and evolutionary processes of humans. This will be particularly valuable in light of the apparent growing complexity of the ancient societies in Eurasia and Oceania. Ian Mathewson, a specialist in population genetics at the University of Pennsylvania, expressed via email that the recent findings are notably intriguing and align well with the evolving understanding of the intricate and interconnected family tree of human evolution. He challenges the concept of introgression events by indicating that it may no longer be apt to speak of such events when they appear to be the standard rather than the exception. Moreover, he emphasized the notion of complexity by suggesting that the currently proposed models are merely a fraction of the possibilities, implying that the actual scenario is likely even more intricate. With just 8 models examined, Mathewson suggests that the reported findings present a feasible hypothesis, but underscores that the true nature of the situation is possibly even more multifaceted. As new fossil findings continue to emerge in the field, recent advancements enable the assessment of updated models against the human genome through specialized programs. According to Schreiber, the effectiveness of deep learning in investigating human origins stems from its ability to effectively analyze intricate models, This approach allows for a more comprehensive examination of the complex interplay between fossil discoveries and genetic data, thereby enriching our understanding of human evolution. If you are an anthropologist aiming to create an intricately detailed model to determine the timing of introgression, whether it occurred 80,000 years ago or 40,000 years ago, a deep learning approach possesses the capacity to achieve this level of precision. This approach empowers anthropologists to delve into the historical timeline and identify the specific time frame when introgression took place. Delving into the intricate web of interbreedings in ancient Eurasia, we find that it represents merely a fraction of the larger narrative of human evolution. According to Bertrand Petit, the potential for unveiling additional uncharted segments of our history lies in the application of advanced deep learning technology. In discussing this method of analysis, he anticipates a plethora of novel findings.